So another very important topic in functions are composite functions. This is basically combining two different functions such that the output of one function becomes the input of a different function. So in that graph that I showed you previously, which looked something like this, we would have it look like this. So the inputs of the first function, which become so the inputs for the first function become outputs for the first function, which become inputs again of the second function, which then goes into the function and gives out the output of the composite function. Right? So you have this entire chain, and this can go on forever if you keep adding functions. So basically, if I had two functions, g of x and f of x, I would make it a composite function between this could be g of f of x, which basically signifies that the outputs, as in all the values of f of x, becomes the input values for g of x. And it can also be written as g of f of x or gf of x. It can be used the other way around also, but these two mean different things, as the over here the outputs of g of x becomes the inputs of f of x and vice versa. Now what would this look like for a normal function? So now let's say f of x was x squared and g of x was 2x plus 5. So now in this first case, I have g of f of x. Okay, so we want to know what that would be equal to. So now f of x is x squared, and whenever I want to put an input into a function, I would write it as something like this, right? Where I would put 2 inside the function here, over here. And that's exactly what I'd be doing in this case. So, but instead of actually putting in a number, I'm putting in the function of x. So that would just be g of x squared. And so when I put that in to the function, I'd have something like that being put in to the input values of g of x. So it would look something like 2 into x squared, because I'm inputting x squared in x plus 5. So now, as you can see, what you basically do in a composite function is to input the rule, so to say, of the function into the inputs of the other function. So basically, you replace x with whatever polynomial or function that's written here. So now, let's say we had to do f of g of x. Now it's the same thing. So we do f of 2x plus 5. And what we're basically doing is squaring an input. So that would be equal to 2x plus 5, the whole square, which you can simplify then. And if you notice something over here, it's that, so now let's say we had a function g of f of x. Now you realize that the domain of this function should begin with the domain of f of x, because we can only input, because all of these x values that we input would have to pertain to the domain of f of x. But now the range of f of x would have to be a subset of the domain of g of x. Because if this is not true, then there can be some values that f of x spits out which cannot be inputted in g of x. So we would always have to, so even if the range was bigger than the domain of g of x, we would have to reduce the range down to it becoming the domain, a subset of the domain of g of x. And this notation here is the notation for a subset. And then we'll have the range of this function to be the range of g of x under this subsetted domain, and the domain of it would be f of x, such that the range would be a subset of the domain. Something that we need to know is inverse functions. The inverse is basically anything such that you do the operation with it to itself, that when you do the operation of something in its inverse, let's say the operation was this dot. So a into a inverse the operation should always give you the identity of that operation. So in terms of functions, this is how we would define what an inverse is, that this operation is the composite and the identity would be just having x itself. So we would say that the composite of the f of x and the inverse of f of x would give us the identity, which would be x itself. Now, what does this really mean if you wanted to visualize it? So we would look at it as kind of reflecting the function. So now let's say I had a function that looked something like that. Okay, what we would do, I mean visually, would be reflected along the line y is equal to x. Now this is not how we define it, but this is what happens to it conceptually. And this is because, and I'll explain to you why that happens in just a minute. So if you had something like this, then its inverse would be the exact reflection of it. And the reason for this reflection is that we want a value, so at a certain value x, we would want that value as an output that when inputted gives out the same value, am I right? So if let's say we inputted this value, so what we're kind of doing is like basically exchanging the x and y for the inverse. And when we do that, so for this value we would get this, for this input value we would get this output value, and then as we exchange x and y, this would come down to here, right, as an output value, and for that output value it corresponds back to that same input value. And because of this, it turns out to be a reflection, because the output over here should be equal to the input over here in a way. And so that's what inverse functions are. And how you would find them is basically, again, I told you, you would just replacing the output and the input such that the outputs become the inputs and they give out the inputs, right? So now let's say I had a function f of x is equal to x plus 5, just for now. Let this be equal to y, let's say. So now I want the outputs to become the inputs and the input to become the output. So let's make this in terms of x equal to y, some function of y. So we would make that 2x is equal to y minus 5, and then x is equal to y minus 5 upon 2. So now we have x in term, we can find x in terms of y. And now what we would do is just say that the inverse of x, and now we just replace the x and y literally, and we get that, and this would be the inverse of this. And as you can see, what we've basically done is replaced this by this, and that makes it the inverse, which is basically what I said we would want to do to get for this to be true. Now, as you saw initially, I didn't take that x square, and the reason is that we can have an inverse only for a one-to-one function, because obviously if I had something like x square, which would be a parabola, now if I had to replace the x's and the y's, as I had said that we do in an inverse function, I would have to get something like this. And if you remember what I had told you about relations and functions, is that this fails the vertical line test, which means it's not a function. And so if we want an inverse function for another function, it would have to be a one-to-one function, because in any such reflection, this one-to-one function would only pass through one line again. And if you think about it, it's because we're saying that this has to end in 1, so we have a many-to-one function and a one-to-one function. And then we're saying that we're replacing the inputs and the outputs, so we then get a one-to-many function and a one-to-one function again. And so this cannot be true. I mean, this cannot occur if the inverse is a function. But what we can do to still get an inverse function is restrict the domain such that it is only a one-to-one function. So for this, y is equal to x squared. If we restrict the domain to x is greater than 0, then we just have this. And that is a one-to-one function whose inverse would look something like this. And it's something that you would have to see is that the domain and the range get exchanged the same way that x and y get exchanged. So for f of x, the domain of f of x would be equal to the range of f inverse of x, and the range of f of x would become the domain of f inverse of x. And now the last thing that we will do in this is what a rational function is. I think that models an inverse proportion is known as a rational function. So now we could also have a rational function in the form of y is equal to x minus 2 upon x plus 3, because this can always be written in the form of a plus 1 upon plus b upon x plus 3, which is an inverse relation. And we just need to know what the basic graph of a rational function is. And so if we just look at y is equal to 1 upon x, so now as you remember, we can never have the denominator be equal to 0. So at 0, so the domain of this function is everywhere but where x is equal to 0. And if you notice this function, as x becomes really small, for example, as x is 1 upon, let's say, 0.1, then it's equal to 10. But when x is 1 upon 0.01, it's equal to 100. So as x becomes smaller and smaller, y starts increasing. So we would have something that looks like this. And then as x becomes bigger and bigger, for example, 1 upon 10 is equal to 0.1, and 1 upon 100 is equal to 0.01, it starts becoming smaller and smaller as x increases. And well, we haven't looked at x being negative, and it's kind of the same thing, except y would always be negative whenever x is negative for just 1 upon x. So it would look something like this. And that is the basic graph of y is equal to 1 upon x. And now, as we add, so this function can always be written in a form like this. And as we have a function such that y is equal to cx minus a upon dx plus b, so like I said, the denominator can't be 0. So we would have to look at where this is equal to 0. So dx plus b is equal to 0, dx is equal to minus b, x is equal to minus b upon d. So at minus b upon d, there would be something known as an asymptote, which is a place where the function doesn't exist, if it's just a point. And then it would have the same basic graph. Yeah, and then we would also have to know where the function is equal to 0, and the function can only be equal to 0 when the numerator is equal to 0. So we would say that cx minus a is equal to 0, x is equal to a, cx is equal to a, and x is equal to a upon c. So at a upon c, the function is equal to 0. And well, if you look at this, as y tends to 0, x cannot exist, because this 1 will never become 0. It will get very close to 0, 1 upon x, but never actually reach 0. Now this is because if I look at the inverse function where x is equal to 1 upon y, again the denominator becomes 0 at some point. And at that point there would also be an asymptote, but that would be a horizontal asymptote, such that and that is because this function can never approach 0 either. And in the same way, we would have a horizontal asymptote. So one way of doing it is to find the inverse. So we want to get x in terms of y. So we would get something like y times dx plus yb is equal to cx minus a. And then yb minus a plus a is equal to cx minus y dx. We take x common, we get c minus y d is equal to yb plus a, and therefore we get x is equal to yb plus a upon c minus yd. And now again, c minus yd can never be 0. So at the point where c minus yd is equal to 0, that is where y is equal to negative c upon d, which would be, let's say here, there would be another asymptote. Because like I said, this can never be 0, and so at that point it wouldn't exist. And now again, as x becomes really big, as x becomes really small, as dx plus b becomes really small, that is, as dx plus b approaches 0, um, and it would reach 0 at minus b upon d, it would become really big. So we would have something like this. And again, it would decrease as dx plus b becomes larger and larger, and will look something like that. And again, we would have to look at it when dx plus b is negative. That time this entire function would be negative, and it will look like something like that. So here we have seen how we can find the horizontal and vertical asymptotes. And I made a mistake there. It should have been something like this, because like we said, y would be equal to 0 where x is equal to a upon c. And so now we have seen how we can find the x-intercept, the asymptote, and how we can draw a rational function of this form.